Hello, in this video I'm going to be solving exercise 2.4.101 from section 2.4 of Jiří Lebel's notes on Diffy Qs. So a mass of 2 kilograms is on the spring with spring constant k newtons per meter with no damping. Suppose the system is at rest and at time t equals 0, the mass is kicked and starts traveling at 2 meters per second. The question is, how large does k have to be so that the mass does not go further than 3 meters from the rest position? Now, for these kinds of problems, it's always very helpful to draw a diagram of what's going on. So let me draw our block with the spring, and then I'm going to draw another block over here corresponding to when the block has been kicked. So let me tighten up the spring, and then here is my block. And over here, there's been a kick by this boots right here, and it pushes the block this way. It was given in the problem statement that at this initial kick, the block gains a velocity of 2 meters per second. And so if the kick is happening in this direction, then 2 meters per second with an arrow like this. And over here, this is going to be my rest position. And so now with the setup, to go about figuring out how large k has to be for this property to hold, what I'm going to do, well, first thing we need to do is we need to determine what the motion is at time. So here, let me write it like this. So first goal, determine position at time t. So we need an expression for the function x of t at time t. And for this, let me go up here and start drawing some number lines. So here, it's convenient to set the rest position to correspond to 0 on our number line. And over here, so the block was kicked a little bit, so 0 is probably right here. It'll also be convenient for us to choose the direction of our number line, or the positive direction, to correspond with the direction in which the block initially moves. So over here are going to be my positive numbers. So to indicate that, I'm going to draw a plus right here. And so then at time t, this is supposed to be x of t. And so now what we want to do is find an expression for x of t. Now, in general, the equation we need to use is mx double prime plus cx prime plus kx equals 0. Where here, there's a few constants. M is the mass. C is the damping factor, or the friction is another way it's presented. And K is the spring constant. So we don't know K, but we're given that M is equal to 2, right here, 2 kilograms. And we're given that C equals 0 because there is no damping happening right here. So I'm going to set M equal to 2 with M equals 2 kilograms and C equals 0. Our equation is the following. Is 2x double prime plus kx equals 0. Now to solve this, well, we can see that this is a second order linear homogeneous constant coefficient ODE. So we can solve this using characteristic equations. And so that's the approach I will take here. Setting up the characteristic equation, it's going to be 2r squared plus k, just k, sorry, equals 0. And it's not difficult to see once we solve for this. So we're going to get r equals plus or minus I roots k over 2. Now let me denote this constant right here in front of the I by omega naught, so that our roots can now be written as plus or minus I omega naught. Then the general solution for our ODE is x of t equals c1 cosine omega naught t plus c2 sine omega naught t. And now what we need to do is figure out what these constants c1 and c2 have to be. Now, this is where we need to come back and make use of the data that we were given about the spring. So at time t equals 0, the system is at rest, right? And I chose being at rest to mean that we're at 0 in the number line. Therefore, we have in symbols that x of 0 is equal to 0. Over here, the initial kick, at the instant it was kicked, it gains a velocity of 2 meters per second. And so because we chose this direction over here, and maybe I should make this look more like a plus. There we go. Because I chose this direction coinciding with the velocity to be the positive side of my number line, this tells me that x prime at 0 has to be 2. So, and we can add the units if we like. So therefore, plugging in these initial conditions, well, first if we plug in 0 directly into our function, the sign's going to vanish because this becomes 0 and sine of 0 is 0. So we get c1 cosine omega naught times 0. But this is just c1 cosine of 0, and this is just c1. So already this tells me, so I can plug in c1 equals 0 to my general solution. And this term is going to vanish, and all we're left with is c2 sine of omega naught t. Taking derivatives to plug in the next condition, we get omega naught c2 cosine omega naught t. And so if we plug in 2 equals x prime at 0, we get omega naught c2 times the cosine of omega naught times 0, which just gives me omega naught times c2. And therefore, c2 is equal to 2 divided by omega naught. So my solution to this ODE is evidently x of t equals, well, now we just plug in c2 to this new form of our solution. It's going to be 2 over omega naught sine of omega naught t. Great. So this is what our solution looks like. And so now let's return over here and remember what the problem is asking us to do. So the problem wants us to determine for which k do we have the property, or no, rather, how large does k have to be so that the mass does not go further than 3 meters from the rest position. Now, it's important to note that it cannot go further than 3 meters in either direction, either in the positive or negative direction. So assuming, for example, that this is 3 meters, our block cannot go past this line, for example. But when the spring pushes it back this way, then if this is negative 3 meters on our number line, our block cannot cross this line over here either. But what this means is that our solution x of t has to be between 3 and negative 3 for all times t. And so going to a new page. In symbols, what this says is we need x of t to be between negative 3 and 3 for all times t. Right. Once again, that's because if we pretend that these are the barriers for -3 and 3 meters, x of t cannot go further than 3 meters in the positive direction, but it also cannot go further than 3 meters in the negative direction. So it must be between these two lines. And symbolically, this just means that x of t is between -3 and +3. Now notice this is equivalent to, just from properties of the absolute value, this says the same thing as the absolute value of x of t should be less than or equal to 3 for all times t. But what is the absolute value of x of t? Well, going back over here to our solution, if we plug it in, we get 2 over omega naught sine of omega naught t, which is these guys are positive. Omega naught is positive just from how we defined it. So we let it be the square root of k over 2, which is positive. So the absolute value of 2 over omega naught is just itself. And then we're left with the absolute value of omega naught, of sine of omega naught t. But the absolute value of sine is always less than or equal to 1. So this is always less than or equal to 1. And therefore, this says that x of t is always less than or equal to 2 over omega naught. And now just plugging in back what omega naught is. So remember, it was the square root of k over 2. So this is 2 root 2 all over root k. Just for multiplying the top and bottom by the square root of 2. With this property, it follows that, or I'll phrase it differently. Notice, if we have that 2 root 2 over root k is less than or equal to 3, then just kind of working in reverse from our work up here, well, we know that x of t is at most this number, 2 root 2 over root k. But then if we can make this happen, then we will also have that this is less than or equal to 3. And then we would have that x of t is at most 3, which is exactly what we want. So now the question becomes, and I'll write this in red. For which values of k do we have that 2 root 2 all over root k is less than or equal to 3? Well, this just amounts to solving this inequality. So if we solve this right here, dividing both sides by 3 and multiplying by root k, we're going to get 2 root 2 over 3 equals root k. And then squaring both sides, oops, I forgot inequality. We're going to get 4 over 9 times 2 equals k. Not equals, less than or equal. Or in other words, 8 over 9 has to be less than or equal to k. Thus, the mass stays between -3 and 3 whenever we have that k is at least 8 over 9. And these are the range of k values, therefore, that solve our problem. All right, that's it for this video. If there are any questions, please feel free to leave a comment. Otherwise, I will see you all in the next video.